Hello, this is Dr. Stephen Jones. We're looking at Chapter 7, the first part of linear programming within this module. We're going to be looking at graphical and computer methods of doing linear programming, and we'll be looking at applications within Chapter 8. So, if we're going to look at linear programming, or LP problems, as they're often described, we're looking at a different way of considering the concept of programming. This is mathematical programming. It's not computer programming like in BASIC or any other computer language. I know there's plenty of them out there, but that's not what we're looking at. Although we are using computer methods, software, to be able to help us to solve problems out there. And so if we're looking at a linear programming problem, essentially what we want to do is to either minimize something like cost or maximize something like profit. And those are not the only things that can be minimized and maximized out there, but that's just a good way to look at examples to it. There are some level of constraints. You can't do everything because you have limitations on the amount of resources that you have available. There are different courses of action that are open to you, that there's not just one way that something has to be done, and that there are ways to find equations, something's equal to something else, or inequalities, something has to be greater than or less than something else. So we can't spend more than $500, so budget is less than $500, less than or equal to $500, or budget is equal to $500. You have to spend $500 on this project, or you have to go 2 weeks on this project, whatever it would be. So if we're going to formulate our linear programming problem, we need to understand, obviously, what the problem really is, make sure that we've defined it correctly, what the objective actually is, so we don't start pursuing something that we think is the objective when it's not. We have to correctly identify what the constraints are and how much they're a constraint, and is there a direction to that constraint? Again, equality or inequality. What are our decision variables out there? What are the things that are going to flip this out there? And then how we can use those decision variables to create the mathematical expressions that we get to put into our computer program. We'll be using Excel Solver for this. So if you have not downloaded Excel Solver, the solver add-in for Excel, you need to do that for the problems that you're going to be using in this module. So one way that you look at an LP problem could easily be a product mix problem, like making tables and chairs, or butter and meat, or something like that. In other words, you have two things that need to either be produced or consumed, and there are constraints on how much of one you can make because resources for that also would be resources for the other. And in that way, what you want to do is maximize something. So if it were tables and chairs, you might be looking at maximizing the profit you can make, because tables and chairs are going to cost customers differently. You can sell them for certain amounts of profit or sales, and if you made all chairs or if you made all tables, you might be less efficient in the use of your resources, and you might not be maximizing how much profit you could actually make out of it. So let's take a furniture example for this. And so it's got inexpensive tables and chairs that it produces. Tables take a certain amount of labor, 4 hours of carpentry and 2 hours of painting and varnishing. Chairs take carpentry and painting and varnishing. So 2 different kinds of labor go into it. And that is what we're looking at as constraints here. carpentry and painting and varnishing are looked at as separate labor amounts. Now, in these constraints that you're looking at, you don't have wood, which is often the option. You know, it takes 6 hours of labor and 4 feet of wood to make a chair, and it takes 10 feet of wood and 10 hours of labor to make a table. And that's set of constraints out there. So that's not what we're doing this time. We are looking at tables and chairs, but we're looking at hours of carpentry and hours of painting and varnishing. And then you have only so many hours of carpentry available and so many hours of painting and varnishing available, perhaps because there's different numbers of laborers in those two different areas, or perhaps because the paint and the varnish, while it's an inexpensive table, that's an added expense to it, and we have to limit the number of hours we can put into it. Or maybe the facility for doing carpentry is larger than the facility for doing painting and varnishing, and so there's only so much time we can put in each one. And then there's a difference in profit, so that a table has $70 in profit and a chair produces $50 in profit. And so the tables are more profitable on a per unit basis, but they also take up more hours of labor. So you can create a table that puts all that information in there. You could create this within Excel, and that's what I would encourage you to do, because you won't be able to use Solver within Word or PowerPoint or something like that. Your objective here is to maximize profit. Remember, profit is in the bottom row there. You want to maximize it while you have constraints for carpentry and painting and varnishing and available hours out there. And so your decision variables are the number of tables and the number of chairs. That's what you're trying to calculate out. Now, you can use linear equations, which when I was learning linear programming, that was the first way we did it. You'd actually algebraically calculate these things out, and it could get extremely difficult, because unless the professor did a very nice job of making certain things, certain numbers easily roundable, etc., you'd come out with 11/62 and whatever. So being able to use software like Excel or other programs certainly makes this a whole lot easier to calculate out what the correct numbers are. Okay, so we have these mathematical relationships that you would see within within an Excel spreadsheet, or that you would put into linear programming matrix if you wanted to do that. And you've got your constraints at the bottom for carpentry time, and you would also have the same thing for painting and varnishing time. You'd have a similar kind of inequality out there. So this is what you would see. Okay, so each table plus each chair, in terms of how much painting and varnishing time that you have out there, takes away from the 100 hours. So those are your constraints. You would then try to be sure that you've set this up as non-negative. In other words, you can't overproduce tables and then have negative numbers of chairs that get produced. Well, if I produce a -4 chairs, I can produce more tables. Well, you can't do that. Okay, I mean, from a mathematical standpoint you can, but you can't do that from a logical standpoint. So we've got ourselves the variables and the constraints, and we can start plotting this out, one way to do that is graphically. If we do that graphically, we start creating lines, and one way that you have to create those lines is to find, first off, where your intercepts are, your y-intercept and your x-intercepts out there. And that helps you to be able to plot. Are there 0 points within this? And you can do that with some of your constraints out there. Where do you get zeros? So if you took something like this where you did no tables, you only did chairs, you'd actually do the math in this way, and you'd come out with 80 chairs. Or you'd come out with 60 tables. And so you find those slope intercepts right there, where if you're making only tables, you make 60 tables and no chairs, or if you make only chairs, 80 chairs and no tables. Well, that's one line, and anywhere along that line would fulfill the function of the 240 hours worth of carpentry. But you also happen to have a constraint on here with you have a constraint on here with the painting and varnishing, and that's not included in here. Now, as I said, anywhere along that line or under that line keeps you with the 240 or less hours worth of carpentry that you can use. This is the painting and varnishing, that if you have only tables produced, you could do 50 tables or 100 chairs and still meet within that constraint. But remember, it's not the only constraint. You have both of those constraints that are out there. And so as you graph this, excuse me, as you graph this, you actually should show the effect of those two lines together. Okay, so if you did only, if you only looked at the carpentry, then it would follow along this line right here. If you only looked at painting and varnishing, it would follow along this line here. But anything that would follow along this line right here is outside this feasible range, and anything that falls along here is outside this feasible range. So only, only on these nodes here, here, and here are you actually within range when you look at both of those constraints together. That does not mean you've got the solution just yet, but it does mean that you're starting to remove other possibilities out there. So you've reduced down what some of the options are for solving this problem. Now, corner point method is what we use. As I was trying to show you there, corner point method is what we're using quite often, because typically the extreme points or the corner points of this are going to be the ones that not only fulfill the constraints, but also are going to be the ones that produce the most profit. Now, here's a problem. We don't know what that point is. And it might be one way that we are going to solve this problem out. We know 0, 0 does it. We know that 0, 80 does it. We know that 50, 0 does it. Those are corner points here, but there's a corner point right here as well. These are not going to anything in here will not violate the constraints, but it's not going to efficiently use all the hours of labor that we have in both of those constraint areas. So you will not be able to maximize the profits either. It's going to be somewhere along here and mathematically we can show that it's going to be typically at one of the corner points. Now, not all the corner points are going to produce the same amount. In fact, it's unlikely that they would produce the same amount of profit. But at least we know where to look. And 0, 0, if you produce nothing, is definitely not going to use up all the labor, but it's also not going to bring you any profit. So you could probably drop that one out very, very quickly. So you can try to use mathematics to calculate this out, and that works perfectly fine. And if you wanted to do that, you could then solve these simultaneous equations. And if you go back to your algebra, and when you had to do simultaneous equations, you'd find that by doubling this equation out there, you actually then are able to put that in here and solve for C, and it comes out that C here is 40, and if C is 40, then T is 30, and that's what our point here is, where T is 30 and C is 40. Now you might say, well, that's what it exactly looks like. You just go up to 30 and you go across to 40, although it looks a little more like 42. Okay. But you can't just eyeball it like that. You actually have to come up with what the numbers really are. And sometimes it's going to lie in an area like there. And then you're going to go, does it look like it's 22 and 44 or 43? So you would actually calculate it out using simultaneous equations. And that, as I told you before, is how I had to do this when I was in my MBA program back 1.5 million years ago. Okay. Now, if you created another table out there where you actually looked at, once you've got those corner points, you've got 0, 0, 50, 0, 0, 80, and 30, 40. If you used those and you put it into the profit equation, remember you get $70 for each table and $50 for each chair. And if you solved for that, you'd get 0 plus 0 is 0. 70 times 50 is 3,500 plus 0 is 3,500. 70 times 0 is 0 plus 50 times 80 is 4,000. You put that there. Or you could do the 70 times 30, that's 2,100. And 50 times 40, that's 2,000, or together it's 4,100, and that happens to be the optimal solution. Now, please don't misunderstand and believe that this point is always going to be the point that makes the most money. That's not necessarily true. And you may have a time, because of other constraints, where you may have 3 or 4 or 6 along here, and you wouldn't be able to say, well, that one right there is the one that does it. Again, you got to do the math to be able to come up with those calculations. Also, there's some level of slack that comes out as a result here. So if we do what we just said that we were going to do, except we decided not to produce as many for this reason or another, we'd find ourselves with a certain amount of resources not being used. There may be a reason for that. You might be able to find a different way to use the carpentry time or the painting and varnishing time, or perhaps somebody's sick and you wouldn't necessarily be able to use it. So slack is one of those resource constraints out there where something's not being used as much as it ought to be. And surplus, in case you were looking at a constraint so that you exceed one of the other constraints out there. Now, if you use Excel Solver, you can limit slack and surplus and take a look at all the constraints that the same time and try to maximize or minimize your objective function out there by using Excel. And you can do that with linear programming problems, integer programming, non-integer programming, and a certain number of variables. Now, we're not going to do anything with 200 variables and 100 constraints in this class, and I'm sure that you're thanking me right now that that is the case. But we will actually solve a couple of problems here. And in fact, one of the videos that's posted up for this module is me using Excel Solver to solve a problem to help you see how to do exactly that. But we're going to do this within PowerPoint first, and then take a look at my video so you can see in real time how I was trying to solve the same kind of a problem. So, Flair Furniture here, you see the constraints and the objective out there for it. And if we're going to use Solver, then we have to put this information into an Excel spreadsheet and then call up the Solver add-in. And again, if you don't have it, you need to actually do this so you can use Excel Solver to help you solve these problems out there. So you'll start putting in constraints. Now it's relatively easy if you want to do this with certain cells. You don't have to make it look like this with this function and these shadings and these fonts, etc. But what you would want to do is to attempt to create a table that is easy to read. One, because it's going to make it easier for us to be able to grade your problem that you turn in for your assignment. Two, because it's going to make it easier for you to see which data it is that's supposed to go into which box within Excel Solver. Formulas that are used within there are typically sum product. So the equal sign, the function sum product, where it allows you to multiply, say, the 70 times the 4 and the 50 times the 3, or whatever it is you were going to do that. That's not what you want to do within this, but sum product allows you to designate a series of data points that will be multiplied against another series of data points. And when you do that, you don't have to say 70 times 4 and 50 times 3. You would actually do the 70 through 50 and the 4 through 3, and it knows it's going to do that multiplication. It's not going to accidentally cross multiply out there. Okay, so you can go through the spreadsheets slides yourself here. I'm going to briefly go through it to lessen the time that we're here in this chapter, and because you can actually see it and read it yourself. And you can see me actually doing it. But going back to the sheet here, the function that we're going to be using is the Excel Solver. And once you've created your table out there and you've created the constraints and put the numerical data in, you click on the Data tab within your Excel spreadsheet. You decide, is this a max or a min? Are you maximizing, like maximizing profit, or minimizing, like minimizing cost? And then what are the variable cells? If you go back here, what are the variable cells that change? That is the number of tables and numbers of chairs that are going to be produced. And what are the constraints? You'll put the constraints within this box here, and those are the constraints of a certain number of carpentry hours and certain number of painting hours, and a limitation on how many hours you have available. You also need to be sure that you don't allow any negative variables, so there's no negative tables and no negative chairs that are out there. And then we're going to be sure that it understands we're doing a simplex LP or linear programming function out there. And as I said before, you could put your cell references in there, and I'll show you how to do all of that with the other video where you can watch me actually doing each one of these things. And there's also videos out there on YouTube showing how to do that. I just happened to solve a problem that's very much like the one that's in your assignment. So you should be watching mine as well. Okay, so once you do that, Solver then calculates out that your best option is 30 tables and 40 chairs, and create yourself $4,100 in profit. And that's exactly what we did mathematically within the, using a reduction of equations, came up with 4 different nodes. Well, it did that very quickly, and it only takes it seconds to do, and it will take us longer even if you use a calculator out there. So if you're going to do a minimization program, sometimes instead of a maximization one, sometimes it's going to be because you want to minimize cost, you might want to minimize waste or use of a certain kind of resource out there. And there are certain kinds of cases within LP when you just can't get to what that answer is that you're wanting it to be. One of them is no feasible solution, one's unboundedness, one's redundancy, and then alternate optimal solutions. So let's take a look at those. No feasible solution is a situation where you may have constraints that work against each other, where because of, and we'll see one here, because some of the constraints are not workable with other constraints, you come up with no way to be able to come up with a good solution to it. You find yourself that way sometimes within life. You want to exercise more and you want to get more sleep, and exercise takes away sleep time and sleep takes away exercise time. I know, I'm being silly, but that's the kind of concept here, is that they may work against each other. And if you take a look then graphically with that, that third constraint is what's working against it. That you could, with the first 2 constraints, you could get a solution, but the third constraint throws it all out of whack, makes it completely unworkable. So if you come up with that, you're going to have no feasible solution whatsoever. Unboundedness means there's not an optimal solution because it's almost like it's free. If you're telling people breathe air, I'm going to charge you for the air that you breathe. Well, unless you have a way to limit the amount of air that's out there, people can just walk outside and breathe air. And so if you find yourself in that situation, it's because the way the constraints are written, it's a completely open thing. You don't have a way to have a limit on the side. So there's no limitation out here, so it goes all the way out to past the end of the page. And because of that, there's no limitation for what profit you could generate. And that's not generally reality, but in a situation like this, if those were your constraints, then there is no solution, because infinity is your solution out there. Sometimes you have a problem with redundancy. That is, one constraint is completely ignorable because the other constraints, one of those constraints speaks for the one that is redundant. And graphically you could show that to be where this is a redundant constraint, because the feasible region is going to be here, and all it says is that this x has to be less than or equal to 25. Well, if it meets along these two lines, especially falls in here, then it's definitely going to be less than 25. So you don't need that one because it's already meeting that constraint. And so that one becomes redundant out there. And then you also have the possibility of alternate optimal solutions, that two or more possible solutions actually provide the same amount of minimization or optimization possible out there. And if you look graphically here, the constraints that are placed as to what the feasible region are, you actually get multiplication out there as to what's available as good choices. And as a result, then there's not a specific best solution. Most situations you're not going to be facing that, but there are some business decisions that could show up where either there's no good solution, there's infinite good solutions, and there's more than one good solution, and you can't figure out which one is necessarily the best. Move along to Chapter 8.